So hello students, welcome to this particular lecture. So this lecture will talk about, or we will discuss more on the CMOS simplified, or the simplification of the CMOS transistors in terms of the width and the length scaling. Especially if you have two or three CMOS transistors, whether it is an NMOS transistor or a PMOS transistor, how do we get an equivalent simplified circuit and then estimate its current or whatever the output node voltage? So we will have, we'll look into one such example in this particular lecture. And then the other part of the lecture, we will talk about the pass transistors, which is also, it's kind of called as a different family, but it is, the fundamentals or the concepts is actually derived from the CMOS transistors. So we will look into the pass transistors, as well as finally we will have a look into the transmission gate, which is nothing but made up of the NMOS and PMOS transistors. All right. So till now what we had seen is the long channel current model, the short channel current model for the NMOS and then the PMOS transistors. And also in the last lecture, we had realized the inverter DC characteristics and then the transfer characteristics, right? Okay, so let me pick up a pointer so that it will be easier for me to explain. Okay, so let's say that we have one transistor here. So this is what I'm pointing to, where one transistor with the input is VDD, and it's an NMOS transistor. There's no bubbled gate here, so that's why it's an NMOS transistor. And it's a standalone transistor. What I mean by a standalone is it is not connected to any other part of the PMOS transistors or any other part of the circuit. So it is a single NMOS transistor where one side it is connected to the VDD and another side it is connected to the ground. What it implies is on one side which is connected to the VDD, it should be the drain terminal. The other one which is connected to the ground, it should be the source terminal. And this is the input. It is supplied with the VDD value. Okay. And we have one more set of configurations where we have two transistors, two NMOS transistors, even this is NMOS and then this is also NMOS transistors. And, they are in series. So again, just to reiterate, it is not PMOS and NMOS, it is both of them are NMOS. So two of the NMOS transistors in series, right? And one is connected to the VDD, the other terminal is connected to the ground. And in between terminals are tied together. The input to this particular first transistor is an A transistor, and the input to the, the second transistor is a B transistor. And both of them are supplied with the VDD potential. So basically what it means is this particular configuration, the inputs are tied together and then they have been given the input of VDD. All right. So now what we have is one configuration here, the first configuration, and then the second configuration. The first configuration, the input is VDD, the input is VDD. And we have a transistor configuration, although the number of transistor configuration is only one transistor. And then we have, this is one rail, this is another rail. So we have a VDD rail and then a ground rail. And then here it is only one transistor. So I'm going to write it as 1 TR, one transistor. The input is VDD. So we have now the input supply as VDD. The two rails has one transistors in the configuration. The rails are VDD and 0 rails. Similarly here in the second configuration, we have two rails, VDD and then ground, VDD and then ground, VDD and then ground. The input is VDD and the rails are VDD and ground. And then here we have nothing but two transistors, 2 TR. Right, so two configurations are there. Right, so let's see what is the overall current that is flowing from the configuration 1 and configuration number 2. Okay. So I'm calling this, this particular configuration number 1 as the C transistor. So that's why I am annotated, or the input is the C. The second configuration, the inputs I have annotated it as A and B. The reason is there are two transistors. One transistor we will label it as A transistor. The another one transistor we will label it as B transistor. This one, the first configuration, we will call it as the C transistor. Okay. The first one is, out of the two configurations, the first one is kind of very easy to realize or understand or, write down the current equations. So let me start with that. Let me begin with writing the current equation for the first transistor, first configuration. So I'm writing IDS for the C transistor and I'm writing it as saturation region. Right? Let's see whether this transistor will be in the saturation region. If I look into the terminals, drain and source, and then the input C, or rather, the input is VDD. The VGS here is VDD. The VDS here is VDD. So VDS value, VDS for the transistor C is actually greater than VGS, which is also VDD, minus VT, which is, let's say, we can consider it to be 0.3 volts. Right? So in this case, if this satisfies, the transistor will be in saturation. So the C transistor is in saturation and is equal to beta of the NMOS, divided by 2 into VDD minus VT the whole square. So VGS minus VT, VDD minus VT the whole square. Right? I have told here it as nothing but divided by 2, but also I have written here as divided by 4. Okay, I'll come back to that. Now let's begin with the second configuration. The second configuration, we have the transistor A, the transistor B, and then we have supplied the rails are VDD and then ground. So in between there will be, if there is a current supply here, if there is a current that is flowing from the VDD to the ground, then there will be a potential called as Vx. So this VDD minus Vx, that will be the drain to source, which will enable the current to be driving in this particular transistor A. And similarly, this Vx to ground will enable the current to be driven in this particular drain to source of the transistor B. Okay. Okay, now let's see in this particular transistor A. So if I write it here, transistor A, on one side it is VDD, okay, and on the other side it is Vx potential. The current here is, I'm going to write it as IDS of A, and what should be the transistor operating region, whether it should be in the linear region or whether it should be the saturation region. The input applied to the transistor A is nothing but VDD. Alright. So if that is the case, the VGS value for the transistor A is nothing but VDD minus Vx. Right. The VDS value is also VDD minus Vx. So the transistor here in this case will have or will be operating in, again, saturation region. The transistor A I'm talking about will be operating in the saturation region because VDS is greater than VGS minus VT. So that's what I have written here. The IDS current for the transistor A is in the saturation region. Okay. Transistor B, if I look into closely, the input is VDD. So VGS is nothing but VDD. Vx is there, which we don't know what is the value of the Vx. So VDS for the transistor B here is Vx minus 0. Okay. Is it possible that the Vx value can be greater than VGS minus VT? So that is the question. So what I meant was the transistor A should supply some current. The same current should go to the transistor B. Right, because both of them are in series. So that's why I have stated that transistor A current should be equal to transistor B current. Although I have written it as linear, let's see why it should be in the linear operating region and not in the saturation operating region. Right? For this transistor B, if it has to be in the saturation operating region, transistor B has to be in the saturation operating region, Vx value should be greater than VDD minus VT. Right. So the moment Vx becomes VDD minus VT here, VDD minus VT, right? What it implies is this is VDD minus VD. Transistor A input is VDD. So VGS for the transistor A turns out to be less than VT. Okay, let's pick some particular values. VDD is 1 volts, VT is 0.3 volts. If Vx is actually more than VDD minus VD, that means if it is not 0.7 or 0.6, it is actually more than 0.7. So it is 0.8 volts. Input to the transistor A is 1 volt. So VGS for the transistor A turns out to be 0.2 volts. So transistor A will be in cutoff. If I want transistor B in the saturation mode, then transistor A turns out to be in the cutoff. So there won't be any supply of the current. Right, in our initial assumption, what we had said was Vx will reach to a value such that it will drive the current from drain to source for the transistor A, and then it will drive the current for the transistor B also. So there will be a non-zero current that will be flowing that will determine the potential of Vx. Okay, so if I want some non-zero current, this Vx value cannot go beyond 0.7 volts. That means it cannot go beyond VDD minus VT. So it has to be less than VDD minus VT. If that is the case, transistor B will always be in the linear region. All right. So the reason is if Vx is always less than VDD minus VT, then VGS for the transistor B is VDD minus VDD minus 0, and VDS here will be for the transistor B will be less than VDD minus VT. So this VDS value will always be less than VGS minus VT, and thereby the transistor B will have a linear region. Operating region is linear region. So if I now equate these two current equations, VDD, the betas of this particular transistor multiplied by, if it is the saturation region, so I'm going to write, so let me write it here. So IDS of the transistor A has to be in saturation. So this is beta for the transistor A divided by 2. Transistor A VGS is nothing but VDD minus Vx minus of VT the whole square. Right. And then IDS of B will be nothing but VDD minus, it will be in linear region. So it will be beta into VDD minus VT minus Vx by 2 multiplied by Vx, right? So that will be the linear region transistor B current. So I will have actually beta A and beta B, right? The dimensions of this transistors, which is given as W by L, W comma L, W comma L here, right, are same. So if the dimensions of the two transistors are same, assuming that the T oxide is also the same, right, the mobility of both the NMOS transistor for a given particular technology node is also the same. So now I have the beta A, the beta for the transistor A and beta for the transistor B to be actually same. So then I can actually, while actually equating the currents for the A transistor and B transistors, I can actually neglect the betas, and what we have is nothing but this particular expression. So we will have this particular expressions when we equate the current for the transistors with the same dimensions of W and the length, the channel length. So from this, I should be able to find out what is the Vx node voltage value, Vx. So Vx turns out to be nothing but VDD minus VT 1 minus square root of 2. Right, so it turns out to be 0.7. So VDD will be, if I pick VDD as 1 volts, VT as 0.3, 1 minus 1 by root 2 is 1 minus of 0.707. So that will be close to 0.3 here, and 0.3 multiplied by 0.7, somewhere around close to 209 or 0.21, maximum of 0.2099 or some kind of voltage I'll get here. So if Vx turns out to be 0.209 or 0.21 volts, so it satisfies our conditions of saturation and linear region. Okay, so for the second configuration, we have got the Vx value, right? So let me once again go back to this particular configuration number 1. Here, the scaling or the dimensions is W comma 2 channel length. So the channel length of this particular transistor is twice the channel length, right? So let's say that, this particular configuration number 2 is designed on a particular chip, and then configuration number 1 is designed on a particular chip. So do two separate chips. So generally, when we are manufacturing on a particular chip or a particular wafer, where we extract multiple chip designs, we tend to have the same channel length. But because I've written two different channel lengths here, channel length of L here for the configuration 2 and channel length of 2L here in the configuration number 1, what just to make it simplified, those two chips or the wafers are completely fabricated separately. Right, so we have this 2 channel length, and then this is the channel length of 1 channel length in the configuration 2. In the configuration 1, it is the 2 channel length with the W. So this current, the current of this particular transistor will be beta C divided by 2 multiplied by VDD minus VT the whole square. That is the VGS, right? But if I want to have, if I want to write this equation in terms of the betas of the transistor A and B, where the betas were same, it was for the channel length of L, and that's why the beta N here, beta N, which represents the transistor A or transistor B's beta value. So that I've written here, right? Because it has a 2 channel length here. So that additional 2 will come here in the denominator, and that's why it becomes beta N divided by 4 into VDD minus VT the whole square. So this beta N is for the transistor with the dimensions of W, L. Since the first configuration has the channel length of 2L, I'm writing this as beta N, which is for the W, L, and then divided by 2. Because, if you remember, the beta is a function of W by L. So L is in the denominator side. So if the denominator, the channel length increases, right, the beta actually decreases. So with respect to W by L, it will be beta by 2, and then additional 2 is coming because of this current equations. All right. Now, if I put, coming back to configuration number 2 now, if I want to find out what is the actual current of this particular configuration 2 when transistor A and transistor B are in series, if I can pick one of the current and put this Vx value, I should be able to find this particular current. So now I have Vx value. So I'm going to input this Vx value into the transistor A saturation current equation. Saturation current generally it's much more simple than that of the linear current, and that's why I'm going to put this Vx node value into the saturation current equation. Hope you have understood this. So going to the next slide, if I put this Vx value, which we have got from the previous derivation, so put this in the current equation for the transistor A, the saturation current. So the saturation current for the A will be nothing but beta N divided by 2 into VGS, which is nothing but VDD minus VT minus of this Vx value, which is VDD minus VT, the whole 1 minus 1 by root of 2 the whole square. All right. So this 1 is there, which will get cancelled with this 1. Okay. And then I'm left with VDD minus VT multiplied by 1 by square root of 2. So which is nothing but VDD minus VT the square, and then 1 by 2, and then beta N by 2, which turns out to be beta N by 4, which is of VDD minus VT the whole square. And if you notice this particular expression, right, which we actually, which came for, which we have derived for the current for the transistor A by putting this particular Vx value, right, into this particular transistor A current, turns out to be same as nothing but the transistor C current. So what we are saying is the series transistors, if I have two transistors of the same dimensions, W, L, and then the next transistor is also W, L, the series transistors can be considered as a greater length of the single transistors. Right, so it's equivalent. So what we did was, I had two transistors, NMOS transistors, W, L, had the same input here. This is same as nothing but having one single transistors of, right, twice the length with the same input. So if the input is VDD here, the same input should go here, Vin. Of course, the same rail should be there, VDD and ground, VDD and ground, right, VDD and ground. Then we can simplify these two series transistors into an equivalent single transistors of W, 2L, where this channel length is considered as the length of the single transistor. So this is nothing but equivalent to L is coming from this L plus this L, right? In fact, what we can actually do is, if I have two transistors, if one transistor has a length of L, the another transistor has a length of 2L, the equivalent transistor can be considered as W, 3L. Okay. And in fact, the one more generalization which we can do is, if I have n such transistors with W, L, W, L, W, L, I can simplify this into a single transistors of W, NL. Right, so this is one such example showing a simplified two series transistors, or the two transistors which are stacked can be simplified to get the current expression by having it as by replacing it or substituting with an equivalent single transistor where the length has been increased. And intuitively it makes sense because, so let me pick another pointer color. If I'm talking about this particular single transistors channel here, and then I'm talking about this particular channel here, and if I'm talking about this particular channel here, if you remember the current for the equivalent, right? So I'm talking about the channel of this. So the current has to pass through this particular channel. Here the current has to pass for channel 1, channel 2, channel N, right? So this is the current that has to see the same resistance, right, which is N times. Here for an N transistors configuration, the N transistors which are actually, if I say 1, 2 and N transistors, for an N transistors which are stacked together or which are in series, the current has to actually see a resistance of N times the single transistor channel resistance, right? So similarly, the equivalent one should have an effect. So this current should also undergo a channel resistance N times that of the single transistor channel resistance. So that's why if I make this N times the channel length, the channel resistance will be N times. All right. So intuitively it makes sense, and for the two transistors also we have got this particular example which which validates that the two series transistors equivalent transistor will have the twice the, or rather the channel length of the equivalent transistor is nothing but the summation of the two transistors which are in series. All right. So the same is true for the three transistors also. So here also I have one configuration where we have three transistors. So W, L of the same width. Channel length is also same. So the same dimensions W, L, W, L and W, L. And what we notice is that we can actually replace or substitute for simplification purpose. We can actually have a single transistor of W, 3L. In fact, we can also do for a long channel model. So this is applicable only for the long channel current model. We can also say that it is W by 3. So the width gets divided by 3, the same channel length. Right? The reason is very, very simple. If I write this particular equation, right? So the current equation, which is nothing but the saturation equation. So beta by 2, right? So in fact, okay, let me try to write it in terms of not in beta. So instead of that, I'll write W C oxide by 3L, because this is the 3L here, right? And then we have this VGS minus VT the whole square. The current for this, the long channel current for this particular transistor also is mu W by 3 C oxide, right? Of course, there is a 2 here, so I forgot that. W by 3 is the oxide divided by L, and then I will write VGS minus VT, the whole square divided by 2. Right, so if I look into both these expressions, right, so the W divided by 3L and W by 3 divided by L, both of them turns out to be the same. So I can also have a dimension, instead of channel length being extended to 3L, I can also have it W by 3 as the width. Just for our analysis purpose, we can as well take W comma 3L, or we can take W by 3 comma L. Right, if I have this 3 series transistors or stacked transistors. Right, hope you have understood this.